Well, I could have just as easily labeled this not a lecture, but an example problem, because it really is just an application of several of the concepts that we've learned previously, uh, and that's the rather famous Sackur Tetrode equation. Um, it was a application of statistical mechanics to give a result that was really obtained independently by Hugo Tetrode, who was a Dutch theoretical physicist, and Otto Sackur, who was a German physical chemist in the early days of the 20th century. In 1912 was the publication date for both of these guys, but apparently they developed it independently. To make you feel really bad on this, when they published their papers, Tetrode was 17 years old, and Sackur, the physical chemist, wasn't much older. He was 22. So obviously, both of these guys were probably geniuses of some order, you know, and makes me and maybe you feel a little bit like a slacker for what all we've done. I know my first publication wasn't at 17, although I did get one at 22, I think, or 21 or 22. But nothing of the quality of this result of Tetrode and Sackur. What they did was to obtain an expression for the entropy of a monatomic ideal gas, which incorporated quantum theory concepts. And if you remember, 1912 is roughly the date that Bohr published his famous Bohr atomic model for the hydrogen atom, okay, which incorporated early quantum considerations. And so they're roughly at the same time. The Sackur-Tetrode equation was considered a major success, explained some nagging problems in statistical mechanics, and but was actually considered a result that led to the acceptance of the quantum theory. I think the statistical mechanics people felt pretty good about, but the quantum theory was still in its infancy. But their result and its application to one problem in particular that we'll talk about certainly helped to turn the tide. I would say probably no doubt both of these guys would have probably gotten a Nobel Prize either in chemistry or physics, but they didn't live much longer after they sort of surprisingly didn't live a whole lot longer after this 1912, not long enough to get the Nobel Prize anyway. And both died in their early 30s, and the Nobel Prizes are not given posthumously, so they lost out on it, I guess, in more ways than one. But for our purposes, it's really just a good way to illustrate some of the application of the ideas to a fundamental problem of statistical mechanics. We'll look at an ideal gas, but really for the canonical partition function doesn't have to be for an ideal gas. This is the canonical partition function for the system consisting of n particles. N is a very large number, Avogadro's number type numbers. And Z1 is the molecular partition function. If you remember, your book calls this small z and this one capital Z over here. And we've seen that we can divide that up in this sort of a hierarchy of more or less increasing energies as I go from left to right. We've got the translational partition function, the rotational, the vibrational, the electronic, or sometimes called the atomic partition function, and then the nuclear partition function. And that's the Z1 raised to the nth over n factorial. And for ideal gas, ideal gas, by assumption, is a point molecule. You're treating the molecule as a point, so there can't be any rotation or vibration or internal degrees of freedom in a point. And so the only thing that survives in this litany up here is just the translational. And we actually calculated that early on in lecture and found this expression. It's going to be a little bit easier to do a little bit of algebra here and manipulate that into this form here. Another equation that we developed earlier was the entropy of the system is kb times the natural log of the partition function for the system, the canonical partition, plus this additional term, which is plus kbt partial derivative with respect to t of the natural log of z at constant volume. And again, like I've been doing, I'm going to drop the constant volume, so this partial derivative says hold the other variables constant, and v is certainly one of the other variables. And then just plug in this for our system partition function, and then do our usual things. This first term I can write as n natural log translation of z, partition function, minus natural log of n factorial. I've also factored out of both of these a kb, so I just have the non-kb terms. So this term becomes t partial with respect to t. And I do the same thing here. I actually took this one step further, and we'll do that on the next one as well. But remember, natural log of n factorial can be written as n natural log n minus n, and then if I subtract that, here I get this would be minus plus. And again, that is a Stirling approximation for the natural log of n factorial, actually minus natural log of n factorial. And it's valid, very, very good approximation for n that are approximating these Avogadro's number of type particles, so for large n. I can do the same thing for this one here. That expands to there using Stirling's approximation. And then just substitute in what we have for the z translational. And that's this expression here and this one here. A couple of things to note is that each one of these has an n in it. And so I'll also factor out an n, and that has no n, and this term becomes, for instance, just natural log, and this one just becomes 1. I'll leave this term the same. And then this term, I'll do two things for it to go to the next line. Partial with respect to t, well, n is a constant amount of gas, and so these two terms, when I take the time or the temperature derivative, vanish. And then this term, I'll actually write the part that doesn't depend on t. That's this piece here. There's no t in this. And then I would have the natural log of that plus the natural log of t to the 3 halves. But the natural log of t to the 3 halves is just 3 halves times the natural log of t, again, using the properties of logarithms. And that makes it pretty simple. This minus natural log, I can move that back inside here. It's just going to be this expression divided by n, and then I still have my plus 1 here. And then this expression, the partial derivative of this natural log piece here, well, there isn't any t in that, so that vanishes. And I'm down to just the derivative with respect to t of this final term. And then finally take the derivative of the natural log of t, that's just 1 over t, and the t's obviously cancel. So I'm down to this top equation here. And then I combine these to make 5 halves. 1 is 2 halves, and 2 halves plus 3 halves, 5 halves. And then this I write as natural log of the exponent to the 5 halves, and so these are inverses here. And that's just so that I can bring this, the natural log of the sum is the natural log of the product, so I can bring this inside. This is actually the form that I generally find it most useful, either this one or this one. Again, capital N KB is the number of moles times the ideal gas constant. We've done that a bunch of times too. So this form 1 is the form that I generally use the Sackur Tetrode equation. However, it seems like just about every book I pick up has a different equation that's equivalent to these. Let me give you a few examples, and then you can read in your textbook in chapter 18 Raph's approach to it, and he's got a totally different equation, but again, you'll find it's equivalent to this one if you spend the time to go through the algebra on it. One way that people will transform these is for an ideal gas, I know that PV is just equal to nRT. And so a lot of times people will solve this for the volume and then just substitute it up here. And then realizing that N is just NKB, then you can get this form too in terms of the temperature and pressure. Sometimes people use the internal energy expression. Remember, for an ideal gas, internal energy is 3 halves nRT, which is 3 halves capital N kBT. And if you do that, you can eliminate T. Let's see what I do here. I divided through by N, and then multiplied through by 2/3, and so kBT from up above is 2/3 U over N. And then you can just plug that into the Sackur Tetrode equation. If you look up here, for the kBT, it's in the 3 halves. And so you get this expression in terms of the internal energy and the volume. And again, that's another form that I've seen people use. In any event, there's a multitude of ways that you'll see it written, and probably if you pick up a book, it might not even be any one of these three ways of writing it. But again, the one I've always found the most useful is this, either one of these first two expressions. Well, we'll turn to an application of it in our next video. But first we have to review a little bit of maybe a concept that you've had before, and that's the Gibbs paradox. But we'll do that in the next video.